Hello.
Hello.
Hi.
Hi. Hi, Emmanuel.
How are you?
Fine. How are you?
I'm good.
So I'm supposed to introduce you.
Yeah.
Can you hear me loud and clear?
Yeah, absolutely.
Okay, then everything should probably work.
Yeah, I'm going to adjust so that I can stand, because I prefer to stand.
Yeah, that makes sense.
And then I'll be ready to go.
Okay.
And can you hear me? And I need to be able to share my screen, I suppose, right?
Yeah, maybe we should check that if it works.
Yeah. Let's see. I'm a bit under the light. Is that a problem or?
Well,
maybe I'll go.
It's okay, but it would be better without.
Yeah, I agree. So the problem is if I don't have the light, is it too dark or is it good?
I think it's okay.
It's okay,
it's
huh?
Better. Yeah, this is better.
Let me get. Maybe I'll put a. Yeah, okay, so I'm going to go like this. And, okay. And then. All right, like this, okay. And then I need to be able to share my screen.
Mm-hmm.
So it's disabled at the moment.
Let's see, is that, maybe it could be that I'm co-host. So...
Yeah, I need to be co-host. I mean, host disabled attendee screen sharing.
So we should ask, I think you were supposed to become co-host, so you can do it. Let's see if.
Oh, okay, so now maybe I can do it.
But I don't know who is supposed to make you co-host. Wait, it seems.
No, I think I
can
can
try
do it
again?
Yeah, I think it's going to work now.
So thank you. Was it Alex or One World Symposium?
Like this? Is it okay like this?
This is perfect.
All right. So I'll leave it like this. So, and I'm going to try to find a light so that. Somewhere.
Well, you can put on the light if it's. It wasn't that bad. I mean.
Okay. I'm going to try to do something. Just bear with me for a second.
Sure.
This should be fine, no?
Yeah, this is okay. Yeah,
Very
definitely.
good. Okay.
Yeah. So I had two, well, one question and one remark. The question was, how do I pronounce your last name? Should I say Cande or Candace?
Candace is good, yeah.
Candace, so the American way, so to speak. Okay. And the other, so I was told that if people ask questions, you might have a co-author or something in the audience.
So I have two. I have Liwa and Yaniv. They're already online. I see them.
Okay, very good. I can see Liwa.
And then they can answer questions. You can do two things. They can answer through the chat, but also I'm happy for them to take the floor in the end if they wanted to, because they are co-authors on some of these things.
Oh, that's nice. So that's up to you if you want to.
Yeah, so I think, like, for example, in the end, if you want to get some question, we could.
So I'll only interrupt you if there is something like immediate, something which.
Yes, absolutely. Yeah, absolutely.
If we cannot understand you or anything like that.
Right, exactly. But I think Yaniv will answer questions, and also in the end they can join me. Since they collaborated with me on some of these things, they can join me in answering questions, so that maybe the community can see who they are and stuff.
Okay, so.
And like maybe we can keep the introduction very short. I think it's.
Okay, well, I have. It's like 2 minutes. Is that too long? Or
1 minute is good, I think. If we
1
can.
minute. Okay, I'll make an abstract for that. 1 minute.
Okay. All right. Thank you.
So there is. Yeah, that's definitely possible. So what is? Well, maybe then I will not say it in the introduction, but I will say it now. So it's actually I feel very happy that you are working on this.
Okay.
I've been saying to statisticians, I've actually been reading about this from the beginning. Like I've known Volodya for more than 20 years.
Oh, I see.
And I've always told people that they should look at this. And 15 years ago, I was really like, at some point we were with a group of people, and everybody was asked to give them their favorite mathematician. So I said Volodya Vovk.
Okay. Oh, wow.
And the others thought, and they were some famous statisticians, they thought I was just crazy. So now I'm very happy that I'm not crazy anymore.
No, I share a lot of what you feel. And so I have a slide where we see Vladimir, like I'll show you.
Okay.
Where is it? The slide? So there's some introduction, but where is this? Oops. Yeah.
So Aditya is another, but he's more recent, of course. I'm working with him now. Yeah, there he is. Yeah.
And I think I think we did a bit of literature search. I think that's the first appearance, right?
I think so. Yes. Yeah, I don't know enough about it. Maybe some similar things were there earlier, but frankly,
of course, it's all so related with like jackknife and stuff that
Yeah. Right. So no, I think that's really where it starts.
I think that's my impression too.
Yeah.
Okay, I'll be back in 1 minute. Just give me 1 second.
Sure.
Yeah, as far as I'm concerned, I'm not as I was not as early as you. I think the catalyst for us were more like people like Jean Lay and Larry Westerman. Like that's how we
Right.
got
Yeah.
here about
I would.
this.
I never worked on it, so I can't claim any. I just read it and liked it. I worked on. I knew it because I have worked a lot on mixability, which is another one of Fosk's big thing, and game theoretic probability. So that's how I heard about it. And then I had to read it because I was a member of a thesis committee of one of his students. So I was forced. So then I became a real fan, but I never worked on it. So I can't. I won't claim anything here. I think Larry Wasserman, he was the first more, let's say, mainstream.
Yeah, that's what I would say. Yeah. Because the early papers are written in a language that is, needs a bit of translation.
Right. Yeah, so there they are. Okay, we have 5 more minutes.
Mm-hmm. So people come to Zoom or they go to YouTube? Like, I know it's also on YouTube or something. I don't know.
We currently have 40 people on Zoom, but that doesn't say much because many more will. I guess people who have registered for the conference come to Zoom, and the rest to YouTube.
I see.
So we'll start in 2 minutes.
Mm-hmm.
I was just getting some emails that for some people the password didn't work. So some people are also watching on the YouTube live stream.
Okay.
Which for them is no big difference. They just cannot ask questions.
Yeah. It's strange. I hope there's not another Zoom problem. Last Monday, it's completely crashed.
Yeah, we had a difficult week.
Yeah. I know I've organized a conference myself in July. I know what you're talking about. It's in general, very strange things can happen with Zoom.
Yeah. The stress level is pretty high because you always fear something bad is going to happen.
I know. But I think we should start.
Yeah.
It's 5:01. Welcome everybody. The next speaker at the symposium doesn't really need an introduction. You probably all know him. Still, I'm going to give a very brief introduction anyway. So Emmanuel Candice started at the École Polytechnique in Paris, then did a PhD under the equally famous David Donahoe. Then he became professor in statistics. He then went to Caltech for a period of 9 years, I believe, and went back to Stanford, where he currently holds the Barnum-Simons Chair in Mathematics and Statistics. And I would like to stress that Emmanuel's research is not just pure statistics, it's really mathematics and statistics. He's probably most famous for starting off compressed sensing jointly with Fields Medal winner Terence Tao. So compressed sensing is now a very big field in its own, very interesting both mathematically and with many practical applications. And well, he has basically won more awards than I can mention here. Let me very briefly say the highest award of the NSF, the Waterman Award, the Polya Prize, a MacArthur Fellowship, and then he's, of course, a member of the American Academy of Sciences and a fellow of the AMS. So today he's going to talk about conformal prediction, which I know from experience is a very interesting subject, and it's high time that more statisticians start working on it. So thank you, Emmanuel. The floor is yours.
Thank you very much, Peter, for the very gracious introduction, and thanks to everyone for tuning in, either on Zoom or via YouTube. I wish I could see you in person, but this is not possible. I hope so that we're going to get through the other side of this pandemic pretty soon, because one thing I really miss are these scientific meetings in person, and I miss non-virtual interactions with my stats colleagues, so I hope I can see you all soon. So as Peter just said, I'll be talking about conformal prediction. It's a very exciting field of research in my view. And I would like to tell you a little bit where we stand today. Before I begin, I just want to thank Rena, Aditya, and Ryan, who introduced me to this field. And so because of them, this has shaped my research in the last year or two. And so thank you. Thanks a lot. So by means of introduction, we could look at machine learning 15 years ago. I actually worked on this. The goal was to predict movie ratings. And honestly, between you and me, whether we get this right or wrong is without consequences, right? But now when we look at, fast forward to today, and we look at applications of machine learning tools, they also call AI in the popular press, but it's really the same thing. We use machine learning to recognize drivers on the street. In the United States, we use machine learning to inform courts' decisions, to assist judge in making decisions about which inmate should get paroled and which inmate should not, and who gets bail and who doesn't. And so I cannot think of a more sensitive application of machine learning ideas. And the stakes are, of course, extremely high, because we're deciding who stays in jail and who doesn't. in the business world, HR departments are, of course, using now more and more machine learning to recruit employees and the young people who may be listening in. Everywhere you look, you hear about machine learning, AI to improve business science. You know, there is a promise that AI will improve medicine and healthcare. And so, of course, we're kind of far away from what people were doing 15, 20 years ago. Now, whether you get your answers right or wrong does really matter. And so with this, we'll talk a little bit about fairness as well. You know, it's been widely reported that machine learning algorithms may be biased against certain groups, and we're going to pay attention to this. But what I would like to stress at the moment is, as I mentioned before, we are entering an application, an era where we use machine learning more and more in very sensitive applications. And I think it's extremely important that as statisticians, as professionals, as data scientists, we'd be able to convey uncertainty and reliable outcomes. I'll give you an example to exemplify my point. Let's say that, you know, a bit like this HR department, let's say that a university is receiving lots of applications. Let's say Stanford receives about 60,000 applications each year, and they would like to automate part of the admission process. And so they might like to predict how some applicants at Stanford admitted. So there might be a quantitative outcome that we're interested in predicting, for example, the GPA after 2 years of undergraduate education. And I may have about each applicant a lot of features: the high school they went to, the grades they got, the courses they took, the SAT scores, their social economic status, their level of physical fitness, information about outside curricular activities, and so on and so forth. And so I may want to learn from the experience of others, have some sort of a predictive engine, and perhaps the predictive engine in this case will return a predicted range, which is 3.62. And what is an admission officer supposed to do with this? How accurate is this prediction? So as we see, we are using now machine learning algorithm that leads to prediction, and these predictions are used to take actions. And so we need to seriously evaluate the cost of getting our predictions wrong. So we need reliable systems, and we need to be able to communicate reliable predictions and the uncertainty that come with them. And the way I think about this really is that what we should be doing, instead of returning point estimates, we should be returning what people call prediction interval. That is, instead of just saying 3.62, you might want to be able to return 3.2 to 3.8. And I want some guarantees about this prediction interval. This is not a confidence interval. We're not trying to estimate, not building a confidence interval around a parameter. We're building a prediction interval about a future observation. And I want this prediction interval to have the property that 90% of the time I'm correct. That is, if I look at all my applicants, and for each of them I build a prediction interval, then I want that this prediction interval covers the true outcome 90% of the time. And that would be a very good natural way to communicate uncertainty so that we can inform reliable decisions. But we don't see prediction intervals being reported very often, and why is that so? Well, one of the reasons, I suppose, is that we're using extremely fancy tools to actually fit for predictive modelings. Random forest, XGBoost, neural nets with so many layers. These models are way beyond past regressions. We don't have formulas to compute prediction intervals and so on. And so perhaps that explains why we tend to underreport, under-evaluate uncertainty quantification. But what we'll see in this lecture is this kind of wonderful field, as I mentioned earlier, of conformal prediction that will let us actually build very accurate prediction interval, no matter what black box you use. And you don't even actually need to know the details of the black box. So as a starter, let's look at a very naive way of building a prediction interval. Again, I insist that we want to predict y, not the mean of y given x. So perhaps what I would do is I would fit a regression function, which you see in red. I would look at the residuals, the deviation from the actual observation from my fitted regression function. And that's what you see on the left. On the right, sorry, I would have a histogram. And to report a predictive interval, I might actually take the regression estimate mu hat and add or subtract the quantiles of the residual. But I know I'm talking to a professional audience. You know that it's a very, very bad idea because we're looking at in-sample residuals and they're way too small. So that, of course, would not work. The residuals I'm getting are much smaller on the training set that they would be on future samples. This is, of course, extreme for neural networks, where I'm sure you're aware of, sometimes people drive the training error to 0, which means that the residuals are all 0, which means that essentially your confidence band would have 0 width. The residuals are much smaller than on test point, and that would not work. So this is where conformal prediction enters the picture. As I said, it was started about 20 years ago. I think that's the first paper discussing the key ideas. And what we've learned from this paper and the vast literature since then is that predictive inference is possible under no assumptions whatsoever, other than having IID data, or not even exchangeable data would suffice. So I want to kind of give you a sense of the major players in this area. The field was largely developed around Vladimir Vogt. He contributed in the late 90s, and he contributes to this field to this day. So there's been 20 years of sustained innovation in conformal prediction. And if you look at his production, you'll see new papers coming about just about every month about conformal prediction. And it's been wonderful to see. I would also like to acknowledge Jean Lay and Larry Wasserman, who realized the importance of Vogt's idea and his colleagues' idea, and basically alerted the statistics community to what was going on in computer science, and also in the process, of course, made fantastic and wonderful contributions on their own. So what's the idea of conformal prediction? To statisticians, it would look quite straightforward initially. What you do, of course, is you do not look at in-sample residuals. You look at the out-sample residuals, and they are bigger than the in-sample residuals. And so when I look at the out-sample residuals, I can actually instead look at the quantiles of the outside sample residuals. And by definition, this means that 90% of the future test point will fall within this band. This can be collected in a formal statement, which is that if I'm looking at the quantiles of out-of-sample residuals, we're going to say that we look at them on what is called a calibration set in the field, which is not used to fit the regression function. Then I can construct the prediction interval in the usual way, and I'm guaranteed to get 90% coverage, or whatever level you set, just by looking at out-sample residuals. Now, you can, of course, this out-of-sample residuals is a form of conformity scores, which is another terminology in the field, S of xy, right? So which measures here the deviation between the observed value and the fitted value. And why do we stop here? We can actually use any conformity scores S of xy. This is kind of a test statistic, if you will. Think about it as a z-score. And instead of just looking at the absolute value of the residuals, we could look at any conformity scores and build a prediction interval essentially using the same recipe, where a point y, a response y, will be included in the prediction interval if its conformity score is low enough. And if you want, if its z-score is low enough. And that, the way they talk about it in conformal prediction would be to say that y conforms to previous values that you've observed. And so the general result from these pioneers is that if I take Q to be the 90th percentile of conformity scores that I've seen on a holdout set, on a calibration set, then your prediction interval, the interval you construct to predict future values of y, will have the right coverage probability. And this is actually an easy result, and I thought I could perhaps walk you through a very elementary proof, which actually takes only 2 lines, is I get to see a bunch of conformity scores on a holdout set for I equals 1 to n, and these are represented with these yellow dots. And now I need to make a guess about yn plus 1. So the conformity score for the n plus 1, the test point, the n plus 1 data point, which is our test point, we're going to just use a very basic property, which is that if the data x, y, y's are exchangeable, or a simplification would be that they're IID, then these conformity scores are also IID. And in particular, the rank of a conformity score will be a discrete uniform random variable. And because I choose a quantile to be the quantile of conformity scores, it's very quick to see that by construction, I'm going to include the point in the confidence interval if the rank of the conformity score for the test point is below Q, which by definition is 90% or whatever level you choose. And so it's a very simple argument. And of course, people in statistics should be reminded of all the literature on non-parametric testing. And it's, of course, very close to this. So now, what do we want to talk about today? So we're going to compute conformity scores. And the question is, it's a bit like testing. Which test statistic should we use? Which conformity scores should we use? And as we'll see that it makes a big difference which conformity scores you build. So in the first part of this talk, I would like to talk about more adaptive conformity scores. So just to a bit illustrate what I'm talking about, suppose that I've got a data set. These are the black points you see on the figure. And suppose that I gave away the problem, which means that the distribution of y given x is known. Then in that case, I can fit upper and lower quantile functions, right? So I would know the red distribution, the conditional distribution. I would know the quantiles of all these distributions. I could connect them. And so I would be able to construct superb prediction intervals. Note that the width is not 0, no matter the sample size. There's uncertainty in y. But what we can see is that the length of the interval can vary greatly with x, because we may have heteroscedastic data. Now, the issue is that in the method I propose, where we actually fit a regression function and then enlarge create a band around the regression function of fixed widths, then we tend to get prediction intervals that do not adapt to x. And we get prediction bands of fixed widths, which may not be desirable, because we know that perhaps the oracle prediction intervals would be highly dependent on your location in X space. All right, so but of course we do not have the distribution of y given x, otherwise there would be no problem whatsoever. We just get a sample, and we want to make inference, again, prediction intervals, without making any assumption on either the distribution of x or the distribution of y given x. So one thing that we found strange at Stanford is that if the goal is to construct a prediction interval, why do you start by estimating the mean? Really, the target is really the quantile of the conditional distribution. So why don't you just estimate this directly? And so, of course, we can do this by this wonderful idea of Kunker and Bassett, which is a few decades old, of quantile regression. And so what we're suggesting here is to bring together quantile regression and conformal prediction. In particular, if you have your favorite machine learning algorithm, be it a neural net or XGBoost or whatever you want to use, what we're suggesting is that you should replace the loss function, the square loss function, with, I like this name a lot, the pinball loss, right? And so people familiar with quantile regression will see that this is essentially when you have a loss that looks like this, you're estimating the alpha's percentile of the distribution of y given x. So just change the loss function from the squared loss to the pinball loss, fit it with alpha equals 0.05, alpha equals 0.95, and you're going to get two quantile regression functions, one for the lowest quantile and one for the upper quantile. And so you can do this on data, and maybe that's a better strategy. But of course, if I fit quantiles, will it work? And the answer is, well, no, it doesn't. Quantile regression has no guarantees of any kind that I'm aware of in finite samples. And so, what we see is we see this on my test example. when I gave the method a fresh test data set, I could see that the actual coverage was 72% instead of 90%. And of course, it can be much worse. Imagine that you're again training neural nets, then essentially your two quantiles will be the same, and so you'll be overfitting tremendously. So we need to adjust these quantiles. And this is what we're going to use ideas from conformal prediction, but perhaps in a novel way, where just as before, we're going to split our data into a training set and a calibration set. On the training set, we're going to use quantile regression to get a sense of where the quantiles of the conditional distributions are. But we know we're not doing a good job. We're not perfectly calibrated. And so we're going to see how well we're doing on the holdout set, on the calibration set. And this is what you see on the right. You have green points on the holdout set, and you're going to score them. You're going to give them this sort of famous conformity scores I was talking to you about. Now, what scores do you get on the calibration set? What we thought of is going to be extremely simple. We're going to measure the distance of a calibrated point to the nearest boundary. And it's going to be a sign distance. So if you're outside of the predicted range, you're going to get a positive sign. So it's going to be the positive distance to the nearest boundary. If you're inside the calibration band, you're going to get a negative sign. So it's a distance to the boundary with a sign which is positive if you're outside and negative if you're inside. Okay, and the details are over here. Now, let's say I have 500 calibration points. I therefore have 500 scores, 500 sign distances. Let's say I want to construct a 90% confidence prediction interval. Then I'm going to look at the 90th largest values of these scores, like the 450th largest value of these 500 scores, the 90th percentile of this score. And what I'm going to do is I'm just going to move up and down my quantiles by this value Q, right? So I'm going to shift the lower and upper quantile functions by an amount Q, which is the quantiles of these conformity scores. So what we can see is if I have, I'm tending to overfit, so undercover, then of course, more than 10% of the point will be outside of the prediction band, in which case Q would be positive, and so I would enlarge the prediction interval. If on the other hand, I started with a very conservative method, and that's a nice thing about this method, which I'm overcovering, then Q would be negative, and I would actually shrink the prediction intervals. And of course, if I started with something that was just about perfect, well, Q would be roughly 0, and I would actually not touch it. So this is how the method works. And when we apply it on the test data you've seen before, then we want 90%, and the actual coverage we observe is 90.01%. Okay, so it seems to work extremely well, but it's not surprising because it's an application of conformal prediction with just new test scores. Now, if we look at how the method performs next to the method I presented earlier, based on the absolute value of the residuals, here we have essentially a confidence band whose width does not change with X. On the right, we have this new method that uses quantile regression, and we get, as you can see, prediction intervals whose width highly depends on X. It's highly adaptive. And so we have a highly adaptive method, while the original method is not. And so one of the benefits that we can see that because of this, we tend to achieve better efficiency. And by that, I mean that the average length of the interval is shorter. So this is to repeat this point again. This is the right plot where I show the length of the CQR intervals, the method we propose, as a function of X. And we can see that it highly depends on X, whereas the length of the original method does not depend on X. And one thing we're going to focus on is the plot on the left, where conformal prediction cannot give you conditional coverage. And that's one of the weaknesses of the method. but you may hope to achieve a form of conditional coverage. And what we see, at least in this experiment, is that the blue method, as a function of x, seems to maintain coverage at level 90%, no matter where you are in X space, whereas the methods tend to kind of overshoot or undershoot, right? So just if you think about finance, for example, and you're trying to predict stock returns and you have measurements of volatility, well, when the volatility is high, your method might actually undercover. When the volatility is low, you might actually way overcover. And so the coverage will highly depend on the value of the volatility. What this method does, the blue method, seems to hold, at least in this example, coverage constant across all values of X, which is important. Okay, so we can look at this on real data as well. And this is a data set where we're trying to use this method to predict utilization of medical services. The goal here is to predict how much of the healthcare system you're going to utilize as measured by the number of visits to a doctor or hospital and so on. And we have lots of covariates, which you can read about, your age, your marital status, your poverty status, your type of insurance, and so on. And so when we look at the performance of these methods, both the original method and the CQR method achieve 90% coverage at a theorem. When we look at length, which is on the right, and conditional coverage, which is in the middle, we can see that this more adaptive method, the CQR method, tends to return intervals that have the same marginal coverage, better conditional coverage, and shorter intervals. So it seems that when you have heteroscedasticity, maybe this is one of the tools, one of the conformity scores you would like to use. So you achieve, again, better conditional coverage, and as a result, you have shorter intervals. This is not limited to the kind of this very interesting data set. We actually tried the method on lots of different data sets, and in lots of cases, we could see that by combining quantile regression with conformal prediction, in many cases, in very different fields, we could achieve better conditional coverage and shorter links. But I don't want to spend too much time on this. Rather, what I would like to do is to expand a bit on how you can build conformity scores. What we've done so far is to leverage quantile regression. And so we were getting sort of naive estimates of quantiles, and where we're moving them up and down by essentially the same amount. We're adding and subtracting the same quantity to the fitted quantiles. What we can do is we can leverage quantile regression a bit more and expand the intervals not in a uniform way. So let me explain how it works. Suppose that now, instead of fitting a pair of quantiles, I fit all quantiles, right? And so I have a bunch of quantile curves, or just a different way to think about this is you fit a conditional distribution function, either via quantile regression or via the wonderful method that Jerry Friedman, my colleague, introduced on contrast trees. You have an idea of what is f hat of y given x, which is a CDF of y at x. Then because you have the CDF of y at x, you can construct a naive interval by just taking the quantiles of your CDF. And that would be a naive way of constructing prediction intervals. Would that work? Well, obviously not. It is not calibrated. So what do you do then? Well, what you can do is you can look at, you have your holdout set, and you have this parameter tau, which is which quantiles of the naive method should I use? And of course, you're going to have a relationship between the row coverage level, the tau, and the actual coverage that you see on a holdout set. And all you're going to do is you're going to pick tau hat, which achieves 90% coverage on the calibration set. And from now on, when I ask you to produce a prediction interval, you're just going to take your naive estimate, not at tau, because it's a wrong value, but at tau hat, which is, in this case, 95%. So you build a family of prediction intervals, and you use calibration to actually understand at which nominal level you should use. And what's nice about this is you can, of course, extend this to discrete labels if you want. And so if you're now trying to predict discrete labels, you might start with an estimate of conditional probabilities. Now, Y is a discrete label given X. And you could get this by the output of a neural net softmax layer, for example. And it would say that, for this value of X, these are my estimated class probabilities, arranged in a decreasing order. Okay? And so if I use a probability estimate and I need to return to you a prediction set, I would say, well, I'm going to include all the largest, the class label with the largest probabilities until I reach the 90%, for example. In this case, it would be ABC. Would that work? Obviously not, because it's not calibrated. But what you can do again is you can use exactly the same method as we've discussed before in the continuous, in the regression case, to calibrate this method in the proper way. And what you would do then, you would say, well, I want 90%, but 90% yields only 85% coverage on a holdout data set. But if I increase it to 95%, I see that I achieve 90%. And so you're going to use the same method as we described, but with a level which is not 90%, but 95%. And in this case, what would happen is you would actually include the class label D. Okay, so you construct a prediction set in exactly the same way by calibrating the coverage that you really want. Now, of course, we're not the first one to before I move on, let's say that maybe for people in the audience, it's not exactly clear how, what are the conformity scores in all these methods, but I can guarantee that they're lurking in the background. And as a result, you just set in motion all the clever thinking in conformal prediction to show that all the methods I've presented achieve exact coverage. So going back to classification, people had, of course, proposed methods to actually deliver prediction sets for discrete levels. And the idea was fairly straightforward, which is you, again, start with an estimate of conditional probabilities of Y given X, and you're going to include Y in your prediction set if your estimate probability is large enough. And what does it mean to be large enough? It needs to be above a certain percentile of the probability scores that you've observed on a holdout set. Now, this is, of course, a very valid method. It will yield 90% coverage, but we can see that it runs into trouble. Again, it's not very adaptive. And so let's look at an example. Suppose we have data points that are easy and hard to classify. So on the left here, I have a label Y, and these are the estimated class probabilities. And we can see that this label is fairly easy to classify. Here I have a label which is perhaps harder to classify, and these are the output of the class probabilities. If the quantile Q is at this level, then in the first case, the method will just return A, which is the correct answer. In this case, the method would actually return an empty set, where I think we can see that we would like to return ABC, but it returns an empty set. And the reason it does this is that somehow, again, the threshold, your conformity scores, is not adaptive to X. But if we were to use the method I proposed before, this method where you actually fit distributions and then you look at the coverage on a holdout data set, what we can see is that by using this more fancy method, so this is like year 2013, year 2020, I'm just contrasting the way you actually build prediction sets, you'd see that in terms of conditional coverage, these newer methods, which are more adaptive, would tend to achieve far better conditional coverage, at least on simulated data. And that's important because you want to be able to tell that for a person with this X, this is your prediction range. even though you lack theoretical guarantees. In practice, you can hope for conditional coverage. And this is something we see on real data. Perhaps I'll skip this, but we of course did extensive data analysis of, let's say, handwritten digits via neural nets. And when we look at these more modern ways of performing conformal prediction, we see better conditional coverage. All right, so I would like to move on, and this talk is organized around slight vignettes. So one was to get better conformity score. The other is to look at where we could apply conformal prediction to do something that is perhaps useful. And so I want to discuss a bit about fairness and the need to treat people equitably. So as I've said before, machine learning, we all worried about the potential biases of machine learning algorithms, and we need to be extremely careful in the way we communicate the results of data analysis to policy and decision makers. Because we want to help people, we don't want to harm people. We cannot do harm. And so, of course, there's a call of action to design machine learning so that it is fair and not biased against any one group. And so just to think a little bit about a sensitive application now where, for example, I need to predict something of importance. The question is, well, as I stated earlier, generally, how do we communicate uncertainty to decision makers and not fool ourselves in thinking that I know the future? Even though I use this powerful machine learning algorithm, there's still tremendous uncertainty about the future. But I think the new point I'd like to touch upon is I have to make sure that we treat everyone equitably. So, of course, there is a large literature in algorithmic fairness, and there's a lot of good work. But what we'll see here is that we're going to depart significantly from this literature. In particular, this literature tends to conflate the statistical problem of predicting risk from the policy problem of taking actions and making decisions. And when you conflate these two things, you can actually end up harming quite a few people. And this point was made by Corbett, Davis, and Goral. So what we're going to try to do is to use actually ideas from conformal prediction to actually communicate what we know about the problem to decision makers in a way that is unbiased towards anyone's group. And we're going to decouple this from the policy problem, because you might actually correctly infer that the chance of an inmate to commit another crime is 20%, but that number does not determine in and of itself a course of action. So how can we use conformal prediction in this setting? So let's go back to the data set that we've seen before, where I'm trying to use machine learning to predict how much of an individual is going to utilize healthcare system. In this data set, I have a sensitive attribute, let's say, which is race. And just as exploratory data analysis, I can actually look at, when I fit my fancy black box my neural nets, I can actually see what it does on subgroups. Now, if I use conformal inference, of course, I'm guaranteed that on average over future individuals, the coverage will be all right. But, I might be interested in looking at the coverage for the non-white group and the coverage for the white group. And when you actually look at things in details, you'll see that, at least in this example, that the neural network tends to overestimate the response of the non-white group and underestimate the response of the white group. Now, in this case, the bias is not too strong, but you can imagine that the application will be stronger. In any case, the fact that you get different answers for different groups and not the same accuracy can be quite hurtful and lead to discriminatory practices. So this needs to be investigated. And so, but again, we can use conformal prediction to calibrate our predictions even better. Let's say I have two groups, just male and female, to be politically perhaps less sensitive. And what we might actually require from our prediction intervals, which will communicate uncertainty, what I know about the problem, is that they be accurate no matter the group you belong to. And so what we can do is we can say, well, what we're going to prescribe is that you run your fancy algorithm, you ran your 100-layer neural nets. whatever I think gives you the best accuracy possible. But in the end, I'm going to be prescriptive. And what I'm going to require is you're going to communicate what you've learned from the experience of others in the form of a prediction interval, which is correct no matter what group you belong to. And so this is encapsulated by these two equations, which means my predicted interval is correct if I'm a male. It's also correct if I'm in a female. So I think this way of communicating what we've learned rigorously quantifies uncertainty and treats everyone equitably. It is unbiased across groups. And I like it because, it's an honest form of reporting. If the interval that I get at the end of the day is long, it says that the model can say little about my problem. I can also observe that the intervals are of different lengths across male and female, and perhaps it's much wider for female than it is for male, perhaps just reflecting the fact that I have less data for female, in which case the decision maker might actually be tempted to collect more data to get more accurate predictions. So now how we're going to use conformal prediction to actually achieve this goal, that is fairly straightforward given everything we've seen so far. We have both a minority and a majority group. The minority group is in orange and the majority group is in blue. And here they are. And of course, I can treat them as separate. And so, that would be a bit naive, but I can always treat them separately and apply conformal prediction to each of these groups. But what we find in practice is, of course, when we learn from the experience of others, it might actually be much better to join the two groups in the training stage. And so you can basically develop a powerful model where all your samples are combined. But when you actually calibrate your predictions on the holdout set, you do it separately for each group. And of course, if you follow this strategy, for people who follow me, you'll see that it achieves the prescription that I mentioned earlier. And so when we actually do this, maybe I'm not going to ask you to look at this table in all details, but we can focus on the last row. This is a method. This is conformal prediction using this quantile regression, where the data has been pulled for training, for estimating the quantiles, but then these quantiles are adjusted depending on the group you belong to. We see that, and again, it's not surprising that we achieve perfect coverage within for each group and short interval lengths. Okay, so there's a way of using conformal prediction to actually do some form of honest reporting. I'm very passionate about this. I recognize that data analysis is not neutral. I think we need to find ways of summarizing information that does not lead to discriminatory or unfair practices. One of the things I'm not sure I like very much about the current literature on algorithmic fairness is it's not my job as a statistician to come up with a decision rule, with an action. What I need to do is I need to empower the user and give the user some tools to make informed decisions that treat people equitably and do people no harm. And so this is what I wanted to say about the very interesting interplay between ideas from conformal prediction and fairness. Okay, so the last stop I wanted to make was about counterfactual inference, where it, again, maybe an application that is familiar to almost any statistician I know, where conformal prediction may play an interesting role. So let me explain this in the last 10 minutes, and then I'll wrap up. As you know, in some form of randomized experiments, patients come in and I can assign them to either a control group or a treatment group, depending on the value of their covariates X. And so in this simple model, you're going to be assigned to a treatment group, given that your covariates are equal to little x with probability E of x, which is known in the field as a propensity score, in which case you become one of these red people. And likewise, it can be assigned to a control group with probability 1 minus E of x. Okay, so people are assigned to either treatment and control. And I'm sure most people in the audience are familiar with the famous setting of potential outcomes of Neyman and Rubin, where, you know, in the word of Rubin, there is a science table, and we only observe, we have a partial view of the science table. And so these are actually the observations we got. We got the response of these treated individuals. We got the response of the control individuals. But there is a counterfactual that we would like to know about, which we did not observe. For example, I did not know how this individual would have responded to the treatment. This is unobserved because this person got the placebo, did not get the treatment, but I might be interested in learning what would the counterfactual be for this individual had he or she received the treatment. And so this is a famous counterfactual inference problem where, again, the dark colors indicate the observed values we get to see. The shaded colors are things we cannot see, but that we would like to know about. And so the fundamental question in counterfactual inference is to understand, or can we say something educated about the value of Y1 for a control individual, that is a response to a treatment for a person who actually did not receive the treatment. And so if you're paying attention to what I'm saying, and I'm sure you are, we have different groups here, and the top groups are the data we have. We do not have any data about the bottom row. And what we can see is we can look at the joint distribution of X and Y on this science table. And so I want to kind of guess these shaded red individuals, but you can see that the shaded red individuals have a distribution of X and Y. Of course, I'm interested in the response to treatment, so the response is Y1. But we can see that the distribution of, you know, the test samples, if you will, is not the same as the distribution of individuals about which I have data. In particular, there's a covariate shift. That is, I would like to learn from these individuals what a typical response Y1 looks like, but I would like to apply what I've learned for the individual to these individuals. But these individuals do not have the same X because they were assigned to a control group. So there's a distribution mismatch, or in other words, a covariate shift that is that we need to take care of. And so we're way outside of conformal prediction all of a sudden. So to make this a bit clear, what we have here is we have the real world, the treated units, and you know, this is a distribution of the covariates given that they've been treated. There's a response. And on the right side, we have the counterfactual words. They have a different distribution of covariates. And I would like to guess their Y1s. I did not observe their Y1s. I would like to guess it, perhaps from what I see on the left. So the general problem stated in the language of conformal prediction is something like this. I have IID sample from a distribution P of X times P of YX. These are the training data. This is what I got to observe. And from this training data, I would like to construct prediction intervals just as before, but for test data that follows actually a different distribution. And the distribution will be different in the sense that the distribution of the covariate X changes between training and testing. So we have what we're going to call a covariate shift, where we have this weight W, which is the ratio between Q and P. Now, in the framework of counterfactual inference, this would be essentially the ratio of propensity scores. All right, so we want to apply conformal prediction, but the examples we've got do not look like the target distribution. All right, so this is kind of the abstract version of conformal inference. You compute conformity scores, you look at the quantiles of these scores, and you put a point in the prediction set if the conformity score for that point is below your quantile. But that cannot work when you have covariate shifts. And so what we showed with Ryan Tibshariani, Rina Barber, and Aditya Ramdas is that there's a slight variation on conformal prediction where you can basically reweight the histogram of your conformity scores to achieve perfect coverage. And so the way it works, it's very, very simple actually. What you're going to do is you're going to reweight the conformity scores you got by reweighting the empirical distribution with the W's, which are the ratio between the distribution between the test group and the training sample. And so now you look at this new quantile, and you're just going to apply exactly the same method, except that your quantile is calculated differently via, if you think about it, a form of importance sampling. And when you do this in the context of counterfactual inference, in the case where you know the propensity scores Wx, you would know how to reweight your conformity scores. And in that case, you get a result that we start to be familiar with, which is that I can actually make counterfactual prediction for a person in the control group. I can construct a C-hat that has a probability that it covers 90% of the time almost perfectly, right? And so this holds in the case where you know exactly how to do the reweighting between the test and the training sample. So it's applicable to randomized experiments which have perfect compliance. Of course, people know that usually I don't know the propensity scores exactly. I might have a good approximation of it. And so if you look at the details of the paper, you'll see that we can adapt to this situation and have a form of double robustness, which roughly says that if you have a good estimate of either the propensity scores or the quantiles of the distribution, then the equation that you see over here at the top holds approximately. And so now you have a very general method to actually build confidence intervals for prediction intervals, sorry, for counterfactual responses. And, you know, again, we can use conformal prediction to do this. We can wrap this again around any algorithm you like, any conformity scores you like. And so if you look at the top 3 rows here, you see we wrap conformal prediction around BART, around boosting, around random forest. And in each case, of course, you achieve exact coverage at the 90% level. If you look at methods that are widely discussed in the literature, they would fail to cover Y1. But with the help of conformal prediction, you can get exact coverage. This is another QQ plot of, now on the right, you see the length of the interval that this conformal prediction methods return in this case. What we can see is, of course, different ways of scoring leads to different performance. So here in this case, random forest appears to be the best method. The blue line here is the length you could get if you knew exactly the right conditional distribution of Y1. And you would not be able to do better than this. And you can see that, yes, you're not on the blue line, but you're not crazy far either. Again, we can demonstrate conditional coverage as a function of X. The top row is what people use at the moment. The bottom row is a method that have been conformalized with some of the ideas we presented. And again, across a range of X, we can see approximate conditional coverage. Now, the work we've done does a bit more, and so this is just an invitation perhaps to open it up for people who are interested in the intersection between causal inference and conformal predictions, where you know, in general, I may have an individual that comes from a population that I've not seen. It comes from a distribution of X, which is Q. I have the treated unit, I have the control units. And for an individual I've never seen, I might be able to say this: I believe that the individual treatment effect for this individual, which in the field is defined by the difference between the response to treatment and the response to placebo, Y1 minus Y0, you would like to actually get a range for this value, which is valid 90% of the time. And the wonderful work of Liwa shows how this can be done via ideas, again, of conformal prediction. So I think it's going to be time for me to wrap up. I think I see Peter nodding. So I had one more stop, but since I'm running out of time, I'll just give you some bullet points. I've not actually discussed a case of data reuse. Like, can we actually reuse a sample both for training and calibration? And the answer is yes, we can. In fact, the conformal prediction has a standard way of doing it, which is called full conformal. The problem is that it's computationally extremely prohibitive, so people don't really use it. I want to put a little plug for the work of my colleague, Ryan Titrani, Rina Barber, and Aditya Ramdas. We've shown exactly how we can adapt the jackknife and cross-validation to have guaranteed coverage so that your data points can be actually both used to actually estimate the quantiles, if you will, and calibrate at the same time. What the paper shows is that the jackknife and cross-validated residuals can fail, but we were able to come up with a modification of the jackknife plus and cross-validation that has exact coverage again. And so this is a bit exciting. Now, when we did this, and again, the big figure of Vladimir Vogt was lurking in the background. The jackknife plus and CV plus are new methods, but they are related to something he did earlier called cross-conformal prediction. And so there's an exciting connection between CV plus, for example, the method we introduced to actually reuse data when sample size is small, and the wonderful ideas of Vogt on cross-conformal prediction. And what's good about these methods is that they can be adapted to any conformity scores you like, whether you have continuous or discrete labels. And in fact, if you look at our papers and our website, you'll see that many cases to boost performance, we're not going to use the split conformal approach that I discussed before, but rather these more refined ideas. Okay, so I'll skip the jackknife plus, just to show you that in the spirit of reproducible research, we try to be good citizens and put some software and examples out that people can reproduce our results and play with code. And with this, I want to thank you for your attention. It was a very rapid tour of conformal prediction. I hope by now you're as enthusiastic about this subject as I am. I just want to reiterate the importance of uncertainty quantification as we're using and deploying machine learning tools to actually in very sensitive applications. And what I really like about the work of Larry Wasserman, Jean Lay, Vladimir Vogt, and all the people contributing to this field is they provide us with ideas that are applicable, in my view, to meet the highest professional standards when we report results in sensitive applications. And with this, I'd like to thank you for your attention.
Okay, well, thank you very much, Emmanuel, for a very interesting talk on conformal prediction. Given the time, I think I am not going to unmute the people who ask questions, but I'm just going to read their questions aloud. So we had a question from Jean-Christophe Morin, who said that I had the impression that in non-technical discussions, fair or unbiased would mean that the outcome of the prediction does not depend on the status of the sensitive variable. But your notion is different. Is that correct?
Yes, it is a different notion, absolutely. So lots of definition of fairness have been proposed, right? And so I think what you are referring to is perhaps something known under the name of equalized odds, where you ask for a certain form of conditional independence between your prediction and the true status. And what we're proposing is completely different. And there are cases, and if you look at the papers we wrote, where we believe that equalized odds can be, it has to be applied with difficulty. So we propose a different notion. What we're proposing has nothing to do with equalized odds. It's just what I want to do is I want to learn. Basically, we do statistics, machine learning to learn from the experience of others, right? And so when I look at past examples, what did I learn? And so I want to be able to actually give a range of values that have the property that 90% or 95% of the time I'm actually correct. And I want this to be true no matter the group you belong to. I'm not trying to tell you, to give you I'm not giving you a decision. The problem with a lot of machine learning is they give you a y hat. They're going to say, the algorithm will say, this inmate will recidivate or will not recidivate. And I find it very problematic because a judge gets something like this. And what are you supposed to do with this? When in fact, you're not sure.
I would like to briefly go also to another question. Pratibha Jagannathan asks, how would we know if a score is a conformal score for a particular given problem?
So any statistic you like is going to be a conformal score if you have holdout data that are somehow exchangeable. So as long as when you're scoring a data point, it's basically things that do not depend on the ordering, right? So as long as when you score a data point, you maintain the property that, if you had IID data, the scores will be IID. This is perfectly valid. So this is where care needs, so it's a very good question. This is where care is required because you cannot just do anything, but you have to make sure that your scores that you get at the end are exchangeable.
Right. And then Sirio Legramanti asks,
for example, the order in which you get to see the data cannot play a role.
Right, that seems clear. You need that. So there's one more question. Why always predictive intervals instead of more general sets?
Very good question. We can build sets as well. And so, for example, if I go back to the method we presented, we can build sets. So, for example, and that's kind of what we were doing when we were doing discrete labels, right? We were looking at, even if you look at the original work of Vladimir and Larry, when you look at, for example, you could say this, you could say, I'm going to fit a density function or a conditional density function, and I'm going to actually include in my prediction interval points for which a density function is sufficiently high. And that actually might actually create, instead of cutting in this way, you would cut this way. And that would actually create general sets. We prefer to stick with, for reasons of interpretability, we prefer to stick with intervals, but you could actually, of course, you can build sets. And that's a very good observation as well.
Yeah, so my personal experience is that if you talk to doctors, for example, you can explain intervals, but not general sets. That's
okay.
will be very confusing.
Yeah. So, but this is a very good point. You can decide to actually retain in your prediction set y values so that your estimated conditional distribution is large enough.
Right. Then final question, very short. Based upon the first part of your talk, can one make a connection between constructing tolerance limits in reliability in those fields and the conformal ideas?
The connection between what reliability?
Tolerance limits in the field of reliability.
Okay, so one thing I want to emphasize, I'm not sure I understand the question completely, but one thing I want to emphasize is that what we can do, and I think that's a limitation of this method at the moment, of course, is I can construct prediction intervals for future observations. I cannot construct prediction intervals for parameters, things I don't get to see. This whole idea is based on the fact that I have examples, and when I have a test point, I have a form of exchangeability. So what we can do is we can actually construct predictive intervals, but every statistician knows that we cannot construct confidence intervals that hold regardless of the distribution of xy for parameters, and that's a limitation. So if the question is about, yes, can you use conformal prediction to estimate reliability in the sense that I want to predict future observations, the answer is yes. But if it's actually to predict a state of a system that I cannot observe, the answer is no.
Okay, well, I think that is actually still a very clear answer. The askers all say thank you. So in light of the time, I think we have to wrap up. So Emmanuel, once again, thanks for a very enlightening talk. I would like to give an applause now, and I think the host live has to unmute everybody for that.
1 second.
Well, thanks a lot for your attention and for staying up late, waking up early, and I hope to see you soon.
Let's give a big round of applause.
Thank you.
Thank you.
All right. Bye-bye.
Okay, so let's start with microphone test. I hope everybody can hear me.
Yeah, very
Live,
good.
Live, you can hear me, right?
Very good.
Okay. Yes, so I guess we can start because we are late. So I will start by sharing. Well, first of all, welcome everyone to the talk by Shin-san. I am Chris Birdsey. I will be the chair for this talk. And first of all, I will share the screen with you. Okay. Okay, so I hope you can see that Shin-san received a very prestigious award. This is in the New Researcher Award from the Bernoulli Society. So let me say a few words about Shin-sun. So he did his undergraduate studies at Peking University, then got his PhD from MIT. He was working with Scott Sheffield, and then he was a postdoc at Columbia University. Now he's an assistant professor at the University of Pennsylvania. It's amazing to me how many fields of mathematics or probability he mastered and contributed to. So there's one group, SLE, Gaussian free field, random planar maps, Liouville quantum gravity. They are sort of related, but on the top of that, he also had papers on uniform spinning trees and abelian cent piles, random matrices. And I've noticed that formally his PhD is from 2017, so just a few years ago. But his list of publications is absolutely amazing. And it starts somewhere in 2012 or 2011. So it looks like 6 years before his formal, his PhD. So that's all I wanted to say in terms of introduction. Obviously, Shin-sun, deserves highly this award, and my congratulations. And I guess we can. I will stop sharing, and I will let Shin-sun take over. For those of you who are concerned with the delay, because we are delayed, according to what I've seen, there is no talk following this. The conference hall is not reserved for another talk. So, Shin-sun, you have as much time as you need to present your talk. And please go.
Okay, thank you, Chris, for the very nice introduction. And thank you, everybody, for coming to my talk. So can you see my screen?
Yes, I can.
Okay, thank you. So today I will talk about quantum delivery theory on the torus. So I want to start my talk by recall some basic fact from two-dimensional differential geometry. First of all, we have this classification of closed topological surface according to the number of holes. So for example, we have sphere and torus and general genus surfaces. And today I will mainly focus on the sphere and torus, but there are some similar stories on heterogeneous surfaces and surface boundaries. And given a topological surface, we can define a smooth metric on the surface to make it a Riemannian manifold. And this metric will induce geometrical concepts like distance, area, and curvature, and so on. And what is the most important concept to us is the notion of conformal equivalence. So two metrics are said to be conformally equivalent if they differ by some local scaling. And here a local scaling can be represented by e to some function on the surface. And in general, this quantum lever theory is a one-parameter family of measures defined on every Riemannian manifold. And this measure will be called a lever field on this Riemannian manifold. It's defined on the space of functions on the surface. And quantum lever theory has two very important transformation rules under. So the first one is under isometry. This one is very natural. It just says that if two Riemannian manifolds are isometric, then the measures are just related by the natural push forward. And the other one is the most important to us. It tells us how the lever measure change under this conformal deformation. And it says that it only differs by a constant. And this is also the reason I said that this quantum lever field is a measure, but not a probability measure, because we want this condition to hold. And this constant actually has the following form. So here, this delta G is the so-called Laplacian Bertrand operator on the Riemannian manifold. And this number is a so-called determinant Laplacian of this operator. So I will not give the precise definition of the determinant Laplacian in my talk, although it will appear several times, but I will just say that this is a number associated with every Riemannian manifold. And this exponent C here is related with this parameter gamma as follows, and this is called the central charge. So I want to say that the first property of this measure is satisfied by every quantum field theory. And the second one is satisfied by every conformal field theory. And this number C is generally called the central charge of the conformal field theory. Before I go to the mathematical definition of the quantum lever theory, I will first give some motivations. So the motivation of lever theory comes from two-dimensional quantum gravity. So here, a two-dimensional quantum gravity on a topological surface S, it just means random geometry on the surface. And this is like the dictionary between the physical terms and the mathematical terms. So the first example of quantum gravity would just be the so-called pure quantum gravity. And this means the uniform random geometry. It models the universe without any matters. And in physics, it is also relevant to consider quantum gravity coupled with the so-called conformal matter fields. And this is a natural way of introducing a one-parameter family of random geometries on surfaces. So given a random geometry coming from the quantum gravity, if we condition on the event that it is conformally equivalent to a particular Riemannian manifold, then by definition, this random geometry can be written as follows, where we have this random function phi on S. In a groundbreaking paper by Polyakov, he introduced the quantum lever theory and showed that quantum lever theory is a conformal field theory. Moreover, he conjectured that this random function coming from quantum gravity, it actually follows the quantum lever theory. And suppose this conformal matter here, it has central charge Cm, then this central charge is related to the central charge of the lever theory by this magic formula. So here, this magic number 26 is actually the so-called critical dimension for bosonic string theory. So after the introduction of quantum lever theory, there are mainly two research directions in theoretical physics about the theory. The first one is naturally the relation between quantum lever theory and 2D random geometry. So here, a Lever quantum gravity is just the random geometry induced by the quantum Lever theory. And the random parameter maps is a very natural discretization of 2D quantum gravity. Then having these notions, tautologically, we have this vague conjecture that Lever quantum gravity should be the scaling limit of random parameter maps. So back to 1980s, this conjecture remained vague because the notion of this random geometry is not really well defined. Nevertheless, there are some very strong supporting evidence for this conjecture because people show that people find agreement in certain scaling exponent in these two approaches. So in the LQG direction, there are something called Kishnik-Polyakov-Zamolodchikov relation. And on the random parameter map side, there are some random matrix techniques. And in any scenarios where the exponent can be computed on both sides, they agree. And on the other direction, so in order to solve the correlation function of the quantum Lever theory, Polyakov and Zamolodchikov, they realized that conformal symmetry in 2 dimensions, it implies very deep algebraic structure of general to the CFT. And moreover, the quantum Lever theory is a primary example of 2-dimensional CFT in this aspect. So although the research back to 1980s about quantum Lever theory remains vague in mathematics, it does lead to a very remarkable progress in probability. First of all, the Lever quantum gravity and in particular this KPZ relation, it gives very deep prediction on the dimension of certain random parameter fractals. The most famous example is Duplantier's derivation of the so-called Brownian non-intersecting exponent. And this is later proved by Lawler, Sherman, Werner via SLE. And in the 2D CFT direction, so Balavan, Polyakov, Zamolodchikov, they argue that 2D CFT give very precise description of the scaling limit of 2D statistical physics models. And one of the most famous example is Cardy's formula for the crossing probability of percolation. And this was also proved around 2000 by Smirnov. So, and over the last 2 decades, so there is an ongoing effort in probability, which is to build a probabilistic foundation for the concept of Lever quantum gravity, scaling limit to random parameter maps, and quantum Lever theory as a conformal field theory. And the current status is that we have achieved a pretty clear global picture with precise theorems, conjectures, and open questions. And my goal today is to present this picture on both the sphere and torus. So I'm highlighting the torus because a few important points will be clouded if we only focus on the sphere. Okay, so let me start by defining the quantum Lever theory on the sphere. So in mathematics, there are 2 probabilistic construction of this theory. One is due to Sheffield and Duplantier-Miller Sheffield. And this is based on the intuition that Lever quantum gravity is a scaling limit of random parameter maps, and it intensively uses the coupling between SLE and the Lever quantum gravity. And another approach is due to David Kopanin, Rose, and Vargas, and they mainly follow the idea of constructive field theory. And so with Aru and Huang, we show that these 2 approaches, at least on the sphere, they agree. And today I will mainly follow the DKRV approach, which is the second one, because it readily extends to torus and heterogeneous surfaces. Okay, so the most canonical Riemannian manifold with the spherical topology is simply the unit sphere on 3 dimensions. And this is the representation of this unit sphere on this extended complex plane. So here, this metric is the so-called spherical metric. And so one of the fundamental theorems in differential geometry is that given any Riemannian manifold with a spherical topology, there exists a diffeomorphism from this abstract Riemannian manifold to the this extended complex plane, so that the push forward of this metric is conformally equivalent to the spherical metric. And we call this diffeomorphism the conformal embedding from this Riemannian manifold to a complex plane. And we know that this conformal embedding is unique modulo Mobius transform on the complex plane. So recall the transformation rules of the Liouville field. We know that in order to understand the quantum Liouville theory on the sphere, it suffices to focus on the unit sphere case. So the quantum Liouville sphere has a very simple relation. The quantum Liouville theory has a very simple relation to Gaussian free field. So I will first give the definition of that. So here, the Gaussian free field on the sphere is just a centered Gaussian process on the complex plane whose covariance is given by the green function of the Laplacian operator. So I will say more about the precise definition of Gaussian free field in the next slides. For now, I just want to emphasize that the Gaussian free field is actually just a random Schwarz distribution rather than a pointwise defined function. So now the Liouville field on the sphere is defined as follows. So we consider this probability measure, which is the probability measure on the Schwarz distribution on the sphere corresponding to this Gaussian free field. And then this measure, it defines the measure on the product space. So here, this DC is just the big measure, and this Q is a constant depending on gamma. And then the Liouville field on the sphere is simply the push forward of this measure on this product space to this Schwarz distribution space by this additive function. So this is the definition of a Liouville field on the sphere. Okay, and so here are some more details on the Gaussian free field. So here the Laplacian operator corresponding to the spherical metric is defined as follows, and this delta is the usual Euclidean Laplacian operator. And now we can define the Discrete energy as this gradient square, and then by the integration by parts, we have this formula. And here, this volume is the volume corresponding to the spherical metric. So then this Gaussian free field has a following explicit construction. So here, because of this formula, we know that the Laplacian operator has positive eigenvalues, except 0, which has eigenfunction constant. And then we consider all the eigenfunctions which are not constant. And then we just taking this sum. So here are a few comments. First, this sum is converged almost surely in the Schwarz distribution space. And more precisely, it's actually converged in the negative indexed subdiv space. And I mentioned that the green function of the Laplacian operator is the covariance of this Gaussian free field. The precise meaning is the following. So we have to take two smooth test functions, and then this covariance of these two test functions is given by this. So I will not give the precise formula for the green function, but I will just say that the green function is equal to minus log x minus y plus a smooth function. So here I have normalized my Laplacian operator to have a 2 pi here, so there's no 2 pi here. Finally, Gaussian free field can be defined similarly on any remaining manifold. Okay, so so now let me define the so-called Liouville quantum gravity. So first, I want to define the random geometry corresponding to the Gaussian free field. So suppose this H is the Gaussian free field defined in the last slides, and then the random area corresponding to the Gaussian free field is defined formally as this. And so since this Gaussian free field is only a Schwarz distribution, this definition doesn't make sense rigorously. So in order to give a precise definition, we need a regularization and a normalization procedure. So here, this H epsilon x is the circle average of the Gaussian free field, which happen to be a continuous function. And then after this normalization, we can show that this limit exists in probability. And this random measure is a so-called Gaussian manipulative calc of this Gaussian free field. And we know that this limit is non-trivial if and only if gamma is between 0 and 2. So we can also define the random metric associated with Gaussian free field. And this is achieved by these two groups of people last year. They were able to construct a random distance function out of the Gaussian free field by a similar regularization and normalization procedure. but this one is much more difficult than the random measure. And you can see the difficulty between the gap of these two work. So today I will not give any details about this random metric, but I will just say one fact, which is this random metric is the deterministic function of the random area. Okay, so now let me define the Liouville quantum gravity associated with the quantum Liouville theory. So here, suppose this X is a sample from this Liouville field measure. Namely, so we sample this Gaussian free field and this constant according to this measure, and then we just add them up. So then the Liouville measure is defined using this Gaussian multiplicative calc. So here it is very similar to this guy, but there are some simple twists. And this metric is just defined by the Liouville measure in the same way as how this metric is defined in Gaussian free field sense. So at this point, you might wonder that, so it seems that this Gaussian free field is already a very nice object. And this metric and measure are defined in a very natural way. So why do we bother to consider this funny infinite measure and define the area this way? So one reason is because, so here, for example, in the definition of this measure, we have chosen to consider the regularization to be the Euclidean circle. But this Gaussian free field is actually intrinsic to the spherical metric. And these two quantities, for example, this volume measure and this radius, they are intrinsic geometric quantities to the spherical metric. So in this sense, this is more natural. And more importantly, this one gives the right scaling limit of random parameter maps, which corresponding to the random geometry physics considered in quantum gravity. So let me start by consider the pure gravity case. So according to Polyakov's prediction, the 2D pure quantum gravity is corresponding to the gamma LQG with the central charge given by this magic number 26. And here, if we solve this equation, we find that gamma equal to this number square root of a3. And since we have a rigorous definition of Liouville quantum gravity, we can make sense of this conjecture precisely. So here we consider a uniform sample of a triangulation with n vertices, and this can be thought of as a discrete version of this 2D pure quantum gravity, because pure quantum gravity just means uniform random geometry. And we assume every face is equidistant triangle so that this is a Riemann manifold. And then we can recall this uniformization theorem and use conformal embedding to embed it to the unit sphere. And this conformal embedding will naturally push forward a random measure and a random distance function on this sphere. So, so here the triangulation is an example of the so-called planar map. And in particular, a triangulation is a planar map where the face degree equal to 3. But we can also define other types of maps. So this is a precise conjecture of Polyakov's prediction on this quantum gravity and its relation to the Liouville theory. So we set gamma to be this number, and then after proper scaling, this discrete random measure and metric on the sphere, they should converge in the scaling limit to this random measure and random distance function defined in the Liouville theory, conditioning on the total area to be 1. Because in the discrete, we have fixed the total number of vertices to be n. And I also want to mention that, so in the sphere case, we have to pick 3 points in order to fix the conformal embedding, but I don't want to go to the detail of this point. This can be made very precise. Okay, and there's also a notion of universality in these kind of scaling limit conjectures for random parameter maps. So one kind of universality is over the type of maps. So for example, we have considered triangulation, but we can also consider other type of planar maps. And another, to me, more interesting universality is over discrete conformal embeddings. So in this picture, we have just used the uniformization theorem from differential geometry to embed this triangulation into the sphere. But actually, there are some other variants of this conformal embeddings in the discrete, which in the continuous should also supposed to converge to this continuum conformal embedding. And here are a few examples. So last year, Nina Holden and myself showed that this conjecture holds under the so-called Cadi embedding. And so on one hand, our work relies on deep understanding of the metric structure of both this discrete uniform triangulation and the random geometry continuum, thanks to these deep works. But on the other hand, our proof also relies on very particular properties of the embedding, so it doesn't extend to any other embeddings. And this question is still open for any other embeddings. And we can also consider the general 2D quantum gravity coupled with the matter field. And here, a conformal matter in the continuum, it can be described in two ways. The first way is a conformal field theory with certain central charge, and the second one is using the SLD. So, but the most relevant to us is discretization, which is simply some 2D statistical physics models. For example, Ising model would corresponding to a conformal field theory of central charge 1/2, and the uniform spanning tree corresponding to central charge equal to -2. And then according to Polakov's prediction, so the continuum limit of the corresponding to this 2D quantum gravity coupled with conformal matter with this central charge, it's given by this gamma Liouville quantum gravity, and the two central charges is related by this magic formula. And in the discrete, this discretization of these quantum gravity coupled with matters will just be given by random parameter maps weighted by the partition function of the corresponding statistical physics models. And for the Ising model case, since this central charge is equal to 1/2, if we plug in this formula, we have gamma equal to square root of 3. And for uniform spanning tree, we will have gamma equal to square root of 2. So now with this table, we can make precise conjectures about the quantum gravity for scaling limit of weighted random maps, as in the uniform case. And so far, this conjecture is not proved for any non-uniform random maps. So weaker variance has been proved for many models in many sense. And so you can find more details in Nina Holden's talk. And there's also a pretty comprehensive survey by Green, Holden, and myself. And the related very important question is to understand the LQG metric for gamma not equal to square root of 1/3. So I want to mention that in this case, there's no counterpart of these very deep works on this metric structure. For example, in this pure quantum gravity case, we know that the metric scaling exponent is supposed to be 1/4, but this is not known in general. And I also want to mention that we have throughout our lecture, we have assumed this gamma parameter is between 0 and 2, and this corresponding to the central charge for the Liouville theory is bigger than 25, and the central charge for the matter is smaller than 1. But very recently, people are starting to thinking about the case where the central charge is bigger than 1. And in this case, the Liouville area measure doesn't make sense anymore because the theory of Gaussian multiple chaos doesn't apply. But the Liouville metric still makes sense. And I will refer to the talks by Green and Holden for more details. Okay, so now let me go to the case of torus. So similar to the sphere case, there are some very canonical torus 2D remaining manifold, which are just the flat torus. So here, a flat torus is just given by the by identifying the direct opposite edges of such parallelograms. And then the uniformization theorem for torus says that given any remaining manifold with torus topology, there will be a tau on the upper half plane, so that this abstract remaining manifold is conformally equivalent to this torus flat metric. And similar in the sphere case, by the transformation rule, in order to understand quantum Liouville theory on torus, we can only just focus on this flat torus. But there is a very important difference between torus and sphere, which is, so given given tau and tau prime on the upper half plane, so these two flat torus, they are only conformally equivalent if tau and tau prime is related as follows. And this means the torus has a very non-trivial moduli space, which is the space of torus metric modulo conformal equivalence. And from this relation, we know that this modular space for torus is given by the quotient of this upper half plane by the modular group. So here, this group is generated by these two transformations. Okay. So now the quantum lever theory on the torus is defined very similar as in the sphere case. So here, since we have flat metric, the Laplacian operator is simply the regular Laplacian operator, and we can define the Gaussian free field similarly. And then we consider this probability measure corresponding to Gaussian free field, and this the big measure on the real line. And then this lever field on the torus is also just this push forward of this product measure. And we can also similarly define the random geometry corresponding to quantum lever theory, which is the gamma lever quantum gravity. Okay. So, and this is the way to define the lever field on a general Riemann manifold. So here we still consider the similar product measure with this Gaussian free field as and the big measure, and then we need to weight it by this term. So here, this Kg is the so-called scalar curvature of the manifold. And since both the unit sphere and the torus, they have constant curvature, you can check very easily that this term is equal to 2qc in a sphere case and just 0 in a torus case. And that's just consistent with our definition of the in the particular case of sphere and torus. So in physics, the quantum lever theory was defined as a quantum field theory with this so-called lever action. And so the way we define the lever field is just the probabilistic realization of this path integral formulation. So here, the correspondence is that this product measure is actually corresponding to this term, and this volume is corresponding to this total area measure of this Gaussian manipulated chaos. And then this lever action will simply by this reweighting of this lever measure. And this approach was first considered in the sphere case by David Companion, Rosen Vargas, and then generalized to other services. Okay, so now let me discuss the scaling limit to random prime maps on torus. So similar to the sphere case, in a pure quantum gravity case, it is modeled by the uniform triangulation of n vertices with torus topology. And we also assume that every face is equilateral triangle. And then, but in this case, the torus has to be conformally embedded to some flat torus with a random moduli. And this will also induce the area measure and the distance function on this random torus. Then the scaling limit conjecture is very similar to the sphere case. So first of all, but we need to add that this random moduli, it will converge in law to some random variable on this moduli space of torus. And then this measure and the distance function will converge to this lever quantum gravity corresponding to torus. So in my opinion, this conjecture itself is not much more difficult than the sphere case. But what is very surprising to me is that there is also a conjecture about the law of this random moduli. And this is actually given by a very simple formula. So this formula remains very mysterious to me. So for now, I can only say that this formula is related to this magic number 26, but I cannot say more than that. So, and there are also some similar conjectures in the case of quantum gravity coupled with conformal matter field. So here, a conformal matter field of a central charge CM is, can be defined similarly as in the lever theory. It's basically a random function on the Riemann manifold. And this measure is related as follows under this conformal definition. And then the partition function of this matter field is defined by the total mass of this measure. And then when this manifold has torus topology, because of this identity, this normalized partition function, it is actually just a function of the conformal class on torus, which is the moduli space. And in general, this measure corresponding to the conformal matter field, it might not make mathematical sense, but this function usually does. And the corresponding conjecture for the random moduli on quantum gravity of torus It's just simply the reweighting of this formula in the pure gravity case by this normalized particle function. And of course, this is also open question from the random parameter point of view. So I want to conclude my discussion on this random geometry part by saying that quantum gravity also induce very natural measures on the moduli space of heterogeneous surfaces. And the quantum gravity intuition, it motivated a very deep relations between the integration over moduli space, enumerative algebraic geometry, and integrable system. Okay, so the remaining of my talk will be devoted to the quantum delivery theory as a conformal field theory. So in this perspective, the most important quantity we want to consider is the so-called correlation function of the quantum delivery theory. And on the sphere, it is defined as follows. Okay. So here, although this x as a perturbation of the Gaussian free field, it does not define pointwise, but this total measure, it can be thought of as a shift of this delivery measure by this Gaussian theorem. This can make perfect sense. And we have to include this so-called cosmological constant because that will ensure that this correlation function is finite for non-trivial range of parameters. And we can also define correlation function on torus in a similar way. So, but here we need to involve this moduli parameter because torus has more than one conformal structures. And the key property of quantum delivery theory as a conformal field theory is the following. On the sphere, it says that if we have these points related by Mobius transform, then the correlation function at these different points, they are simply related by a simple factor. And similarly, if these two moduli, they just related by the modular group, then their partition function is also related by a simple factor. And to see this point, we can think about the three-point sphere correlation function. First of all, so this is the general condition for the boundedness of the correlation function. So here, we have to make every alpha to be smaller than q, and the total sum of this alpha is bigger than the Euler characteristic of the surface times q. And in the sphere case, the Euler characteristic is equal to 2. And if you plug in these two conditions, that means we need at least 3 alpha values in order to have a finite correlation function. And so because of this transformation rules of the of the correlation function, and also because that on the sphere, any 3 points are related by Mobius transform, we can see that this correlation function can be factorized as some very simple prefactor depends on the points, and some function only depends on alpha 1, alpha 2, and alpha 3. And this function is a so-called structural constant of the quantum delivery theory. And in a very remarkable paper by Kupani, Rose, and Vargas, they showed that this correlation function has this very explicit formula. So, and this is a very deep fact about Gaussian multiplicative calculus, because if we look at the definition of this correlation function, the only non-trivial part is coming from here. Other than that, they are just Gaussian measures. Okay, and this formula is called the DUZZ formula because it is previously predicted in physics by DUZZ. So as I mentioned earlier, Balaev and Polyakov and Zamolodchikov, they were trying to compute the correlation function of the delivery theory, and they realized that 2D local conformal symmetries, it implies very strong algebraic constraints on all 2D conformal field theory. For example, we have the so-called operator product expansion. So here on the left-hand side, we have this exponential functions at 2 points, z and 0, where z is very close to 0. And on the left-hand side, it is a summation over only at 1 point. And here, so both of these higher order terms and this exponent, they are some universal quantities which are holds for OCFT. And the only special data for any particular CFT is this set that you are summing over these formulas and this coefficients. Okay, and from here, we can say that this gives a mechanism to reduce from a n point to n minus 1 point by applying this mechanism. And so the so-called conformal bootstrap for 2D CFT is the algorithm to compute all the correlation functions in terms of this spec and this 3-point function following this OP procedure. And for the quantum Lever theory, the basic input is given by these two. The 3-point function is simply this DOZD formula in the previous slides, and this set is given by Q plus IR. So the quantum Lever theory is a primary example of conformal field theory with a continuum spectrum. And many of these conformal matter field in quantum gravity context, they only have a finite spectrum. The most famous example is just this IC model. And so I want to mention that the reasoning of this conformal bootstrap in the previous slides is very hard to make sense probabilistically, because this measure doesn't really make sense, since this P is actually belong to this complex numbers. But the output of the conformal bootstrap are some precise conjectures on the correlation functions of the quantum Lever theory. So here is the example of conformal bootstrap applied to the 4-point correlation function on the sphere. So here, this is the 4-point correlation function applied to these 4 points. And the prediction says that it equals to this integral. So you can see this DOZD formula coming from this OPE exponent. Coming from this DOZD formula. And this function here, this is explicit power series coming from these dot terms. And this power series is a so-called conformal block. And this is universal for all CFTs with the same central charge. And this power series was conjectured to converge in the unit disk. And the conjecture would be that as long as this 4-point correlation function is finite, this formula should hold. And this is, and mathematically, this is another deep statement about Gaussian manipulated case. So in a very recent paper by Gulamon, Kapani, Jose, and Vargas, they showed that when gamma is between 0 and square root of 2, the conformal bootstrap holds. And so they managed to prove it by making sense of the OPE procedure when gamma is between 0 and square root of 2. And this idea extends to general endpoints on both sphere and torus. And then a very natural question is to prove the conformal bootstrap for the case gamma between square root of 2 and 2. So I want to say that this GKIV approach is very robust to extend to endpoints on torus and sphere, but it has very crucial obstruction for this range. But on the other hand, most of the interesting values of gamma from the quantum gravity point of view belong to this range. So in my talk, I have mentioned this square root of a third from the pure gravity and the IC model corresponding to square root of 3, and the uniform spanning tree corresponding to square root of 2. And yeah, so all these values actually belong to this range. And so this is not just some standard open question, but I think it's a very interesting one. And the more open question would be C, DOZD formula and the conformal bootstrap from the scaling limit of random paradigmatic point of view. Okay, so here is another example of the conformal bootstrap applying to torus. And here we need to have this torus parameter. And this function H is the so-called 1-point torus conformal block. So in the torus case, we only need one alpha to have some correlation functions. So this is the simplest conformal bootstrap equation of torus. And this Q is the so-called modular parameter for the torus on the unit disk. And the working progress of GKRV extending their approach to the sphere would show that this conformal bootstrap holds for torus also in this range. So here, both this conformal block on the sphere and on the torus, there are some formal power series defined by the so-called Virasoro algebra, which is the symmetry algebra of general 2D CFTs. And the series coefficient, they can be computed recursively. So for some very special parameters, this conformal block, they have some integral representation. And this is usually good enough for many conformal field theory coming from the matter field of gravity, such as the Ising model. But for the Liouville case, we have seen that all these parameters here has to be generic. So, and in this general case, conformal block is a quite complicated object. And very important aspect of conformal block is its relation to the gauge theory. So in 2009, AGT, they discovered a correspondence between the quantum Liouville theory and certain four-dimensional supersymmetric gauge theory. And in particular, the conformal block, they actually corresponding to the so-called instanton partition function computed by Nekrasov. And this is one example of this AGT correspondence applied to this one-point torus case. So I will not elaborate on this formula, but I will just say that this this is the power series corresponding to the Liouville conformal block, and here on the other side, so you have some summation over these Young diagrams, and this summation is a so-called Nekrasov partition function. And this is my last theorem to present. So in a very recent work, so Gausso, Remy, Ethan, and myself, we gave a GMC representation of the one-point torus block. More precisely, we consider this expectation. So here, this H tau is simply the Gaussian free field on the torus restricted to the unit interval. And this random measure is the Gaussian multiplicative chaos. And then these two functions are some explicit function that I will not give the detail. And then we can define this concrete function when this parameter Q is real. So we have shown that this function admits a analytic continuation around Q belong to 0 and 1, including the origin, which means that this guy give a power series. And we also show that this power series is actually the same as the one given by the conformal block, which is the one here. So to me, this is another interesting fact about Gaussian multiplicative chaos. And as a corollary of our proof, we showed that for gamma between 0 and 2, this series of conformal block, it converged when Q is smaller than 1 over square root of 2. And this number 1 over square root of 2 is mainly due to some current technical constraint. So the correct value should just be Q smaller than 1. And the approach by GKRV, I think they were able to show that this is true, but for gamma between 0 and square root of 2, and they have to assume it is only hold almost everywhere for P, not for every P. So this is a difference between our approach. And so in a working progress, we are trying to show that this modular group, it acts on the linear span of this probabilistic definition of conformal block. And once this is shown, the fact that this domain, it covers the fundamental domain of the modular group, this will imply that this conformal block actually converge on, for every Q smaller than 1. So, and I also want to mention that this GKRV approach, it doesn't extend to even gamma equal to square root of 2 by continuity because of the essential obstruction. But if we combine their approach and our work, we can say that the conformal bootstrap holds for gamma equal to square root of 2. And the future goal of our program is to extend this work in general cases, including the four-point sphere. Okay, so this is pretty much what I want to say. And here is a reminder of a few open questions. And thank you for your attention.
Okay, thank you very much. Leif, could you unmute everyone for a second so that we could applaud Shinsun? Okay, I don't have a response from Leif, so maybe you could use reactions. Leif, could you unmute everyone for applause for a minute or two?
Everybody's unmuted.
Thank you.
Okay, so I'm looking at chat and I don't see any questions, but let me ask a question myself. You see, I'm an outsider, but I'm a little bit more familiar with SLE. And so, you know, that's by now already a sort of classical topic.
Yeah.
But, you know, what I know about SLE is that it works only for a certain range of parameters. And there are certain crucial values of the parameters when something special happens to SLE.
Yeah. Right.
It's a piano curve, just a very simple curve in some range. Then it starts to cross itself, and in the end, it becomes a space-filling curve. So the question is, are there any special values of the parameters in your talk that somehow correspond to those more classical special parameters in SLE?
So I think, yeah, this is a very good question. So in my talk, there are actually two perspectives. One perspective is this random geometry. And in this perspective, so I didn't mention any proofs, but if we go to the proofs, we have to use this perspective. And we can see that in this perspective, we need to use various important couplings between SLE and linear quantum gravity. And so whatever special value corresponding to SLE will give you some special value corresponding to this LQG. And so far, most of the important values of this SLE, they will give important values in LQG where gamma is between square root of 2 and 2. And that's a range where this so-called conformal bootstrap is not proved.
Okay. Okay, so there's a question actually. Can your findings be generalized to any Riemannian manifold from Andrei Strab?
So conceptually, it can be, I mean, so you can formulate similar conjectures in general Riemann manifold. But so the thing is that for higher genus Riemann surface, it's even a very active topic in just the deterministic geometry. So the technicality would grow exponentially once you go to higher genus services, because the modernized space of higher genus services is very complicated. But on the other hand, if you only care about theorems like this, so I'm trying to find. Yeah, so suppose you want to consider conjectures like this, where you do not care about any formulas, then I think for higher genus, it's not so much difficult than the severe case. It's similar to say that any manifold is like locally, it's a Euclidean manifold. So once you know the simply connected case, it shouldn't be too hard to generalize to a general case. But what is more interesting is that once you consider the modernized space, you have these very nice measures. And these very nice measures, they are playing a very important role in mathematics.
Okay, so I have another question. You know, one of the terms that you used in your talk is quantum gravity. Over and over again, but one of the best known current research directions in physics is the string theory, which makes this attempt to somehow unify quantum theory and gravitation. So it's a very general question. Is there any relationship between the two?
Yes, so you can see that in my slides. So this is a mathematical translation of what quantum gravity means. And you can see in this corner that they have this string theory. So basically, so this paper of Polakov is called Quantum Geometry of Bosonic String Theory. So in string theory, there's a very important statement saying that bosonic string theory has critical dimension 26. And the precise meaning of that statement is actually this. So there is a very close relation between string theory and quantum gravity.
So is this 26 like the famous 26 of
this
string
is the most
theory
famous.
that
Yeah, right.
because it's even in popular science, like 26
Yeah.
dimensions and so on, right?
Basically, so this is a paper discovering that the string theory in the Bosonian string theory should have dimension 26, and then later some other people realized that if you introduce a mechanism called supersymmetry, then you can reduce this dimension to 11. So then people start to look at symmetric string theory and I think So basically that's the story.
But in your talk, that 26 is not reduced to 11 by any mathematical.
Yeah, because I didn't consider supersymmetry. So once you consider supersymmetry, it is more solvable, but it is not a probabilistic measure anymore, even not positive.
Oh, it's not even positive. Oh, I see.
It's not even a real number, I think. It's just some formulas.
Oh, I see. Okay. Well, if there are no more questions, well, we already applauded. So let me just say that I enjoyed the talk very much, and I hope that everybody else enjoyed it as well. And thank you very much. And congratulations once again on your award.
Thank you very much, Chris. Thank you.
Okay. Goodbye.
Bye.